Okay. If you can see my screen, can you type a yes, maybe? Can you hear me? Am I too soft? Okay, cool. So today we are going to solve this question, right? So right off the bat, anyone has any ideas how to solve this? Right, anyone has any, I don't know, any suggestions? Yeah, that's one way we can do it. So just as what Sharafuddin said, right, let me just comment this out. Okay, so one of the ways is that we can do a linear search. So linear search meaning I will go front to back or back to front. I will traverse the whole array, right? And Sharafuddin mentioned that we can check index before and after to find the peak, right? I have one question for you, Sharafuddin. Do you think that we have to check before and after? Right, so the question is peak index in a mountain array. And it is guaranteed that our integer array, right, would be a mountain. Right, so for mountain, the length would be more than equal to 3. And there would exist a peak where all of the elements before is strictly decreasing and all of the elements after are strictly decreasing as well. So in other words, if I visualize our array, we would have like a mountain, right? So with all the values. Okay, so my question for you, Sharafuddin, is that do we have to check before and after? If I am the person walking up this mountain, right, how would I know that it's a peak? When I'm standing on the peak and I look forward, it's going down. Then I will be at the peak, right? I don't have to check behind because I know that when I'm going up, it is an upwards motion. So actually what we can do is we can just, okay, he's typing. So this is one of the ways. Anyone have any other methods to solve this? Ternary search. Okay, this one a bit too advanced for me. Maybe you can explain what ternary search is. Right, so actually we can just check the element in front, right? So we can just check index after. And if the index after is smaller, then the current one is the peak, right? Okay, so another way that we can do is to use a binary search. All right, thank you, Jiaxing. So that is about ternary search. Maybe later I can read up on that and anyone else can read out on that as well. But today we can focus on binary search. Right, so this is a very simple binary search question. It is quite straightforward. So what we do here for binary search, okay. So for linear search, I would be walking, I would just go from the front and I'll walk until I meet the peak, right? Whereas for binary search, what we can do is, okay, let me just draw an So for binary search, we actually find the midpoint of the mountain. So let's say this is the midpoint, okay? And we check which interval we want to keep searching in. Right, maybe I draw it on the next page so it's more clearer. Okay, so this is my mountain, all right? So the initial interval would be the whole mountain, all right? And then what I'm going to do is I'm going to find the midpoint, and I'm going to determine which interval I'm going to search. So in this case, I'm going to search for the left interval, right? And in this left interval, I would cut it in half again. And here, now I can choose to search from this and that interval. And I will be searching this interval. And then we can keep doing it. We can keep cutting it in half until we find the peak. All right? So how do we determine which interval we should choose? This is actually quite similar with what we have said just now in linear search. We can check the index after, right? So if I am standing here and I see that it is going downhill from here, then I know that the peak must be behind me, right? So I can just take this interval and search. And when I cut it in half again, okay, I am standing here, and again, I'm still looking forward. Okay, I can see that the mountain is going up, so I know that the peak is in front of me, right? So using this logic, I can keep finding the midpoint and keep finding a interval for me to search, right? So this is the basic intuition behind binary search. So anyone has any questions about binary search? All right, let me see. I think there shouldn't be any questions. Yeah, okay, it's fine. So with this, we can actually turn it into code. So this would be the initial logic behind our search, right? So as we can see that we probably already know that binary search will be quicker than linear search, because for linear search, I have to keep walking the steps until I meet the peak. Like what if the peak is just at the end? Then I have to walk to almost the end, right? But for binary search, I can always split it in half and do the searching, right? So for linear search, the complexity would be O of n, right? Because I'm going through the whole array, n being the size of the array. Whereas for binary search, it would be O of log n, right? So log n is actually the complexity for binary search. In computer science, the base for log is actually base 2 as opposed to base 10 in mathematics, right? So if you want to know more about the complexities, you can do a search on this. There's a lot of articles on Google. Okay, so now we are at the 10-minute mark. I think we can start with a bit pseudocode. But before that, maybe we can start with like a template for binary search. So of course, for different questions, the code will look different, but the overall structure of a binary search is almost always very similar. So if we refer to the picture, the diagram as I've shown earlier, first, we take the whole interval, right? So we can use two variables to mark the intervals. Okay, I will just use an integer called low and an integer called high. Okay, and then what should I initialize low and high with? So we will be using the start and the end of the array, right? So I would just start it with 0, and high I would start it with array, the size of array minus 1, because array is 0 indexed, right? Of course, there are scenarios where the low and high could be different, but in most scenarios, it will start with 0 and array size minus 1. Okay, and then with that, we can start our binary search. So usually in a binary search, we would use a while loop with a base case that would terminate the while loop. Okay, so recall that what we do was that we find the middle point and then we determine which interval we need to take, right? So to determine the midpoint, we can just add them together and divide by 2, right? So we can add low and high and divide it by 2. Okay, let me know if you have any questions in the chat and I will get back to them later. Okay, so what I'm doing is just adding low and high, and I'll divide it by 2. Again, there would be like scenarios where mid doesn't look like this, but very rare. Mid would always look very rare that the scenario that mid will not look like this. Usually, sorry, usually mid would always be low plus high divided by 2. There are like very less cases that is not. Okay, and now we need to determine the, okay, so here let me just write a bit of comment. So here I am finding the midpoint. Okay, and now I will need to determine the interval, right? So if you notice, okay, so let's say if, sorry, let me draw another one. Okay, let's say this is our mountain, and we are at this midpoint. So now we need to determine whether we should take this interval or that interval. So if we take this first interval, right? So this is low and this is high. If we take this first interval, we are actually changing high, right? To make it come here. And if we choose the other interval, so if we choose okay, so if we choose this interval, then we are actually moving low here, right? So changing the intervals are just a matter of changing the values of low or high. Okay, so in my template here, it would usually be some checking, and then you can, change low or change high. And at the end, we will just return the solution, return the answer. So this is like the overall template for binary search. Okay. Let me check the chat for a while. Okay, everything's good. So this is the overall structure of a binary search. And then, now, okay. So with this structure, let's try to find out what our base case is and what checking we need to do to change low and high. Okay, so I think I'm going to give you a little test case. Okay, so let's do 1, 2, 3, 4, 3, 4, 5, 2. Okay, so this would be our test case. I'm just going to write the index down here so I can refer to it. Okay. So in our binary search, our low would start with index 0, right? And our high would start at index 5. Okay. So for the first time, our mid would be low plus high divided by 2. So it's 0 plus 5 divided by 2, which is 2.5. But then we set this as an integer, so it would be truncated, the 0.5. So it would just be 2. Okay. So when we are at index 2, okay, which is the value of 3. So just as our logic in linear search, we can check the index after, right? So we are at index 3, and then we know that the next value is 4, meaning that it is still increasing. So we know that 3 definitely is not the peak, right? And if 3 is not the peak, then 2 and 1 would not be the peak also because it is increasing, right? So we can just remove this from our interval, and we will start with index 3 the next round. So what do we learn here? We learn that if the index after is larger than the value of the current index, then our low would equal to mid plus 1, right? Because we can just start with this. So I think maybe I can just copy and paste this code up here. Okay. So here, just now we determined that if the array at mid is less than array at mid plus 1, all right, in that case, then I would change low. Of course, there are scenarios where, if we go into the condition, we would change high, but in this case, we would change low. So low would equal to, right, so if we follow our logic mentioned just now, low would equal to mid plus 1. Okay? And then, so now low is 4. The value of low, the low is 3, and the value of low in the array at index low is 4. Okay, the value in the array at index low is 4. So next up, I've already changed low to 3. Okay, and then high is still 5. So with low equals to 3 and high equals to 5, mid would just be low plus high divided by 2, right? So it's 3 plus 5 divided by 2, which is 4. So mid equals to 4, which is index 4 in this case. All right. So now we are at index 4. And we are checking, right? So here we are checking the value of array at the mid index and the value of array at mid index plus 1, right? Mid plus 1 index. Yeah. So here, when we are at mid equals to 4, okay, meaning that we are at index 4 and the value is 5. And when we check the value of the next index, which is 2. So 2 is obviously smaller than 5, right? So we know that, okay, by logic, we know that since 2 is smaller than 5, so 2 could not be the peak. Okay. However, there is a possibility that 5 is the peak, right? Because we are not checking the one before, so we don't know. In this case, 5 is the peak. But what if the test case is like this? Then 5 is not the peak, right? But there is a possibility that 5 is the peak. So we should include 5 in our next iteration. Instead of doing mid plus 1, high would just equal to mid. All right. So let me check the chat for a while. I think that, yeah, no problem. Okay, so now we have already established our methods of changing the intervals, right? Choosing which side we should go in our binary search. Okay, now let's work on our base case. So when do we stop the while loop? When do we stop looping? So here we are already at high equals to 5 and mid equals to 4. Okay, so essentially our interval is looking like this. Right? We are looking at these two right now. Okay, index 4 and index 5. Okay, so with this, okay, I hope you can see my text. So low equals to 3. Sorry. In the next iteration, low would equals to okay, let me just write this first. Okay, so low equals to 3, high equals to 5. We checked it already. I think I did it wrong here. It shouldn't be this. Sorry. It's actually this. This is the interval that we are looking for. Okay, so low remains as 3, but we change 5 to be 4. High to be 4. Okay, because of this second else statement where I change high to mid. Right, so I change high to mid because 2 is smaller than 5. Okay, so with this, low equals to 3 and high equals to 4, then mid would be, technically it would be 3.5, but then, the n would be truncated. So mid would be 3. Okay, so at index 3, which is here, the value is 4. And the next value is 5. So according to our logic here, if array at mid is less than array at mid plus 1, I would change low equals to mid plus 1. So low would equals to mid plus 1. So now low equals to 3 plus 1, which is 4. So now low equals to 4 and high equals to 4. And if I continue to do it, it would be an infinite loop, right? Because 4 plus 4 divided by 2 is 4, and we would just continue. However, this is actually the correct solution already at index 4, right? So let's establish our base case. So with this test case, we know that our peak has been found. Okay, so in this case, here you can see that we find our answer when low meets high, right? So can anybody think of a base case that will stop when low meets high? All right, let's see. Yeah, we can definitely use that. So while low doesn't equal to high. Or what we can do is, since low started with 0 and high started with array dot size minus 1, right? So we can also do while low is less than high. I personally think that low less than high would be a much better choice, but low doesn't equal to high works too. Alright? Now, if we look at this question, it says that it wants you to return the index. Okay? So in this case, when low equals to high, it would, sorry, this return should be outside of the while loop. Okay. So we know that when low equals to high, this while loop would exit, right? Meaning that at this point, okay, at this point, low equals to high. So I could just return low or high, doesn't matter. So I'll just return low here. All right. So this is the solution for this question. Let me try to run this to see if there's any bugs. I think there might be a bug because it's running so slow. Okay, we'll see. Low equals to 0, high equals to array dot size minus 1, while low doesn't equal to high. I will set mid. And then if this, low equals to mid plus 1, else high equals to mid. And then at the end, I'll return low. Yeah, this should work. I don't know why it's running so slow. Okay, maybe my laptop is dying. Let me open a new tab and try to do this again. Right, so I assume that you don't have any questions. Maybe I'll just run this and stop this. It's the same, right? I think it's safe. Yeah, so there's something wrong with my laptop. Okay, so I'll just run the test cases. All right, let's just run the code. Yay, okay. So we passed all the test cases. Now, actually this doesn't really matter, but actually there's one thing that we can do that would save this thing, this whole code 2 steps. Is that here, right? So if you read the definition of a peak, it has to have something before and something after that is lesser in value, right? So the peak could not be index 0 and the peak could not be the last one. So we could actually start with low equals to 1 and high equals to array.size minus 2. And because the array length is more than equal to 3, so it is guaranteed that we will not go out of bounds, right? The index will not go out of bounds. So we can do this. It will save like 2 steps, but it doesn't really affect the complexity. Okay. And we can also try low less than high just to show you. Yeah, this works too. Okay, so I guess that this is a small introduction to binary search. You can definitely read out on binary search and ternary search. Just now somebody posted it in the chat. You can go search that. I'm going to read that up later also. Yeah, that's basically it. So to recap binary search, usually we have a low and a high index. Okay, and then we do while a base case. We would find the midpoint and we would determine the interval. Okay, and we would keep doing until the base case executes. Then we would obtain the answer. Okay, so let me see the chat again. Yeah, there's no questions for today. So I hope you guys understood what I said and I hope you guys learned something today. I'm gonna pass the time to our next speaker. Bye, guys. Okay.
Okay. Let me share my screen. Okay, so the problem that we're solving today, it could be said that it's a math problem, okay? It's not that hard. It's an easy question. So this is the question just now, okay? But this is the thing that we want to solve, okay? So this is the problem that we want to solve, lah. It's called palindrome number. So what we call a palindrome is something where we read in both direction, it will be the same. So for example, in this number, 121 is a palindrome because like when you read from the front, it'll read like as 121. But if you read from the back, it is also 121. So this is a valid palindrome. So to give another example, if I have 123, then 321, this is also a valid palindrome because you read from left or you read from right, they are the same. But if I have like this 1 2 3 2 4, then this is not a palindrome because when you read from the left and when you read from the right, they are two different things. So this is not a valid palindrome. Then also there's another case, if there's a negative, it can never be a palindrome because like you cannot read like a negative number, you can't read the negative sign at last, so it's different. So that's why so it's basically very simple. The question is very straightforward. We just want to check whether a number is a palindrome or not. So do you all have any ideas how we can solve this? There are actually two ways that we can solve this. One is more efficient, the other one is still okay, but like can be improved. Let me maybe check the chat, see if anyone has any idea about how this can be solved. Oh, anyways, I can just share about this. Actually, like knowing how to do palindrome is quite important important, I would say, because last time when I go for like an interview, they have a question is about palindrome, and it's a quite important question also lah. But yeah, so there's not. I'll just introduce you to algorithm that we can solve this. So because like for a palindrome lah, like it doesn't always has to be. I mean, it's not necessary number, but for this question, it says it's a palindrome number, so we know that everything is a number lah. But in some cases, this can also be a valid palindrome. Like let me just use this ABBA. Okay, you read from front is ABBA, you read from back is also ABBA. So this is also a valid palindrome. Although we're not going to handle this today, we're only going to handle numbers, but we can handle these kind of cases as well. So there's two ways to solve this. One is that we return this one to one. It's a type integer. Okay, we can turn this into a one-to-one of string type. I would just put it like this to be more easier to see. Then you can do like you can look through it, like you can do some sort like a two-pointer. You can do some sort like a two-pointer. One from the left, and then one you have two-pointer. Then you have like two pointers. Okay, one left and one right. Then you just keep on going to the middle. So you will check like, okay, does the left pointer equals to the right pointer? Okay, then in this case, left pointer is equal to right pointer. Okay, so it's still valid. Then I go to the middle. Then in the middle, then the left pointer pointing at 2, right pointer also pointing at 2. Then 2 is equals to 2, so it will be the same lah. So this is valid. If like this lah, then we know, okay, from the left to the right. So I compare left pointer and the right pointer. 1 is definitely not equals to 3. Then I'll just return false because I know this is not palindrome. So this is one way to do it using string, but this is not the most efficient solution in this case, because like let's say you have a very large number, it's just 1, 2, 5, 4, 3, 1. Okay, so let's say you have this kind of like number, then if you do it as in a string, then you have to check a lot of times, like you have to check like 5 times here lah. Check left, right, and then left, and then right, and left, and then right, and then left, and then right until you meet then you. Okay, so you need to repeat a lot of steps, then only you know that this is palindrome. So another way to solve this is where we can because it's a number, we can do some very fancy math stuff to reverse that thing. Okay, so we can actually reverse this integer. So if we just check, we can reverse it lah. Just reverse. Okay. So let's just say this is reverse. So if we just check original is equals to, then we know already, because like 1 2 3 4 5 4 3 2 1, after reverse we will still be 1 2 3 4 5 4 3 2 1. Then only there can be a palindrome. If it's valid life, if it's not a palindrome. Let's say I have 1 2 3 4. Okay. And then I try to reverse, it will become 4 3 2 1 ma. Then they are not equal ma. So this is not a palindrome. So basically this is easier and this is faster, because when you do math, you don't necessarily have to of like ping. Basically how we reverse number, we just pop out we just do some math. Like we're going to use mod. Mod is like a remainder when you do division there. So let's just talk a bit about the math theory. So let's say if I have how can we reverse this? So I can make this bigger, easier to see. Okay, so how do we reverse? So let's say use my ID. Okay, because this one I can zoom bigger. So let's say I want to reverse 1 2 3 4. Reverse 1 2 3 4. So how do I reverse this? Is that I can keep popping out this number. I can keep popping out. Let's say I wanna get out this number. Okay, I wanna get out. Oh, bro. Okay, let's say I can just keep on pop out this number. Okay, I can pop up 4. Then I will have 4 right? Then I have 4. Then I have 4. Okay, then I move on. I pop out 3. Okay, then now I pop out this. Then I have 3. Then I pop out this. Then I have 2. Then I pop out this. Then I have 1. So basically, if I do that, then I have reversed that the whole number. So this is the process of how we reverse lah. But the question is, how do we get this last number? So we can do divide by 10, okay, right? So let's say if I do divide by 10, this whole thing will be 123, right? So what I can do is, when I do divide by 10, I know the remainder will always be the last digit, because like 123, I know the 0.4 will always be the last digit. So is it true? So I can still go on. Let's say now I want to get 3. So 123 divided by 10, I know it's 12.3. So move on. I know like divide 10 equals 1, 2, and then lastly I know 1 divided by 10 will be 0.1. So you see the decimal 1, 2, 3, 4. So this is how I can extract the last digit. So like in computer science, we have another operation. Instead of divide, we have another operation called mod. So mod is another like a getting the remainder type of operation. So let's say I have 1, 2, 3, 4. I can 10. Okay, this will straight away give me 4, because mod 10 means what is the remainder. So like in this case, this is the remainder is 4, the remainder is 3, the remainder is 2, the remainder is 1. So I can just this. Okay, then I can just do this, and 3, 2, 1. So basically, this is how we can extract a last digit. So just to prove this, so I can run a Python in. So let's say I have 1, 2, 3, 4, right? So if I do divide by 10, you can see it's 123.4. So if I want to get only the last digit, I can do 1, 2, 3, 4 mod 10, I'll get 4. So 1, 2, 3 mod 10, I'll get 3. 1, 2 mod 10, I'll get 2. 1 mod 10, I'll get 1. So essentially, if we read like this, we get like 4, 3, 2, 1. So we reverse this original number. Then we just compare lah, whether 1, 2, 3, 4 is equals to 4, 3, 2, 1. So how do we know this is valid? Let's say we find a palindrome, for example, say 1, 2, 2, 1. Okay. So if I do 1, 2, 2, 1, I do mod 10. Oh wait. Just clean it up. Okay. So I do 1, 2, 2, 1. Then I do mod 10. Okay, I have 1, right? 1, 2, 2, mod 10. I have 2. 1, 2, mod 10. I have 2 again. 1 mod 10. So if you read like 1, 2, 2, 1, it will be equal to 1, 2, 2, 1. So this is how we can like check whether it's a valid palindrome or not. So enough talk. Let's try to implement this. This is not very difficult. So I just write. I'll keep it here. I'll just write the solution down. So it's a function that takes in the number called x. Then like I said, we already know the constraint is there can never be negative. If it's negative, it's straight away won't be a palindrome. So we just check like if x is smaller than 0, then we just return false, because negative number can never be palindrome. Okay, can never be palindrome. So then we do it again. So like continue this theory lah. How we do is we just keep on taking the last digit, then we add them up to become a number. So I'll have to keep track of original number. Just make a copy of x. Then I need a last digit. Okay, so last digit, I'll just initialize it to 0 for now. So so what do? We have to essentially like loop through them, right? So what we can do is so there's one trick here. So if you see 1 mod 10 after you do 1 mod 10 then you know like I'll say wait, let me check. Okay, how to say yeah, okay, we also need like a reverse. Okay, let me just think through how should I put this in word. Yeah, okay. So look at this. We just ignore this for now. But look at this. There's a base case where we can devise is when do we stop? We always stop when we get like a 0 in front. right? Like, okay, so I'll check, okay, I do divided by 10 already. So is 1, 2, 3 bigger than 0? Yes. Okay. Is 1, 2 bigger than 0? Yes. Is 1 bigger than 0? Yes. Is 0 bigger than 0? No. So I stop. Okay. So this is the base case. Okay. I'll keep on doing, no matter how large the number is, like it can be 1, 2, 3, 4, 5, 6, like it can be very large. The thing still applies. It still applies. Like I will always stop when it equals or smaller than 0. Because like 1, 2, 3, 4, not smaller than 0, continue. 2, 3, not smaller than, continue. Until it's 0 or lesser than 0, then I stop. Okay, so this is basically how we do it. So let's say only I want to do this operation while x is still bigger than 0. So what I'll do is I'll first get the last digit first. So I'll get it like this, like mod 10. This is how we get the last digit. So 1, 2, 3, 4 mod 10, you get 4. So then I also have to like add the last digit to the first one. So I'll do like reverse, and then normally I'll do like reverse equals to like reverse plus last digit, right? But is it necessarily true? So let's see. So let's see if this is true. Let's just okay. So let's just do a Python. So let's say I have 1, 2, 3, 4. I do mod 10, right? At 4. Okay. So reverse is initially 0, ma. So like do 0 plus 4, right? So it will be 4 lah. Let me just like let me just create like a variable. So let's say reverse is 0. Okay. So I know reverse is 0. I can print it out. So I have like, let's say x is 1, 2, 3, 4 lah. Yeah, okay. So x is 1, 2, 3, 4. Then if I do x mod 10 is 4, right? So I'll do like let's say reverse plus x mod 10. Okay, x mod 10. So reverse plus x mod 10 is 4. Then the next x mod 10, it will become x mod 10 mod 10. Okay, right? Then it will become like a sorry, I should do x then never mind lah. I think I've just demonstrated lah. So let's say I do x mod 10 reverse, now still 0 because I did it. Just update lah. Reverse is equal to reverse plus x mod 10. Okay. Then now it should be 4. Okay. Then x, I put it equals to x is equals to 1, 2, 3 now, right? So it should be 1, 2, 3 now because I already take the form. So I just update again. Reverse equals to reverse plus x mod 10. Okay, then I should have 7, right? I should have 7. But is this the case? No. Actually, I want 4, 3, 2, 1. I don't want to add like 4 plus 3 plus 2 plus 1. It's different. Having 4, 3, 2, 1 and 4 plus 3 plus 2 plus 1 is a different thing. So I cannot just directly add it. So I have to do some funky math stuff. I cannot just add it like this. If I add it like this, it will become like 4 plus 3 plus 2 plus 1, which is not correct. It will become like, it will become 10 in the end. If you compare 10 is 1 with 1, 2, 3, 4, it's not correct. So what I have to do is I have to do a times 10 first before I do plus the last digit. So why do I mean this is where yeah, I have to like we can test this out lah. So like let's say we go through the first test case. So this is like we know the last digit is 4, right? So something plus 4. So what is this something? Reverse initially is 0. Okay, so I know it's 0 times 10 plus 4 will be equals to 4. Okay, let's do it again. Then at the second test case, now now it's become 4 times 10 plus this time is 3, so it become 43. Okay, then now it is 43, right? So 43 times 10 plus 2 become 432. Okay, then again we repeat it. 432 times 10 plus 1 become 4321. So essentially when we have a times 10 we will keep on expanding. I will keep on expanding the digit. Okay, this is what I mean. 4, 3, 2, 1 is not equal to 4 plus 3 plus 1. So we cannot just do like reverse plus last digit. It will not be the same. So we have to like do the multiply by 10, because it's hard to explain how this works. This is basically just math stuff. It's just math stuff. Okay. This will work every time. So this is what we want to do. And lastly, we want to update the what is called we already have the last digit. We have the reverse ma. So lastly, we want to what is it? Yeah, we have to divide by 10, because we never change x. So like at the first iteration, it will be 1, 2, 3, 4. Then if we don't have this at the second iteration x will still be equal to 1, 2, 3, 4. But essentially what we want is like at the first iteration, x is equals to 1, 2, 3, 4. The next iteration, x equals to 1, 2, 3. The next iteration equals to 2. Next iteration equals to 1. Then the next iteration, like 1 divided by 10 will be 0.1, which is like it's not we don't want to do 0.1. We like but because this is integer so you never get like 0.1. It will just become, so like x, this is already hit the base case we will not continue. So basically this is it. Then lastly what we have to return we just return whether the reverse is to original. This is what we want to do because we want to check whether the original number, like let's say original is 1, 2, 3, 4, and then the reverse number is 4, 3, 2, 1. Then we want to check whether 1, 2, 3, 4 whether 2, 3, 2, 1 is equal to 1, 3, 4. So it's not so return false. So if the original is like, let's say 1, 2, 2, 1, then the reverse is also 1, 2, 2, 1 So 1, 2, 2, 1. So this 1, 2, 2, 1. So then this is equal, so it will return true. So basically this is the whole solution. Let's just import it out, then later we'll do the string version one. String version one is not that hard also. So let me just paste this. Let me just paste this in. Okay. So before we submit let's talk about what's the time complexity for this. So the time complexity for this is that no matter how you have to iterate through each number. So the time complexity is O of it's actually O of like the size of, how to say digits of x, number of digits of x. This is the time complexity So it if you give me like a very big number let's say if you give me this kind of number, the computer can still process very fast one, because this is how many digits, like at most 20 digit 20 digit, the computer only has to do like 3 operation for each digit so it only has to do like 60 operation. And then if you have like a dual core or 4 core or quad core, it can it can do it very fast So no matter even if your number is very, you can still do it very quick. So so basically it's a fast solution and you don't and your memory complexity it's just O of 1. Why? Because you are just assigning few variables, so it will not be as computational expensive as you thought So let's just submit this, and this should work Okay, here we have a problem in C++. So we have the sign integer overflow. So basically what it means is that if you know C++, it tells us the constraint is it will be up to 32-bit. So it will up to negative 32-bit to positive 32-bit. So this integer is not enough to hold that big of an integer. So basically what we have to do is just change it to long, or you can just do long. Not that different So if we submit this again, then we'll see that it works. Yeah, it works. Because if you don't really understand this part is okay. It's not part of the algorithm. It's just that the amount of like the data type can store is already reached maximum. So that's why you need to use long. So I also have the test case here. So if I just run this, yeah, then oops, I have all this stuff here. Okay. If I just run this here, then you can see all the test cases. So let's just implement another algorithm since we have like last 8 minutes. Let me just see if there are any questions. There's any? Okay, no question. Good. So let's just implement a string one and see if how we can do it in string lah. It will be slower if you do it in string, but we can still try. Is palindrome string? So I have like this thing. So I'll have to convert this x to string first. Not pretty sure how we can do this. Convert into string, but it should be very easy. Like in the guess it's not that hard. So there's a toString function. There's a toString method. Okay. Yeah. So toString. Okay, yeah. So there's a toString method that we can use. So we can just say a string as toString x. Okay. Then I'll also have like a pointer lah. Like I'll have like a left pointer which is equals to 0 and then right pointer to s dot size. Very similar to the first question we did just now. So I'll just do while left is smaller than right. Okay, because they shouldn't overlap. While they're smaller than left and right, I'll just like if left equals to right. Okay, I'll just say if left is not equals to right, false. And else, if I can reach the end, I'll just return. Basically, this is what we can do. Let's just test it out. Oh, I forgot a semi. Let's just run it again. Okay, it doesn't work. Okay, let's see. Which part does it? So it fails at. Okay, let's see. Okay. So it fails at. Let's see. So left 0 and then right is say let's take a example for 2 1 2. So left is 1. Left is not right, then equals, and then is equals it will go on. Okay, so maybe I forgot to increment them. Okay, I think someone in the chat just so if yeah, I have to do like left plus and then right minus. Yeah. So stupid, I never thought of that. Yeah, it's still not working. Maybe I need this. If it's equal, then I'll have to do that also. It's not working. Why? Let's just see. Left, right in the condition is just the index. Oh, true. Yeah, stupid me. So I have to index it into it. Yep. Yeah, so it passed. So this is how we can do it lah in a string way. If you would like it's like this one is much more faster lah, because you don't need to create a string then use two pointer to look through this. Basically you just do math lah. Computer is very good at doing math. So like doing math is much more efficient than like doing checks, doing search, to a lot of stuff. Doing math is very close matter. So basically this is the question lah. So let's just test this out. We just try to submit code, so probably this should work lah. And we shouldn't have like the integer overflow problem because we already turned this into a string. So and let's see the runtime. Okay, you see like if when we do math, the runtime is only 22 milliseconds. The string one is 27 milliseconds. You can argue it's not that much of an improvement It's just 5 milliseconds But what if you are processing like 1,000, a million of tests, a million requests every second? That 5 milliseconds really matter. So yeah, so they use not that much of the memory, but you can see that the math one, the runtime is faster It sometimes even get like 21 milliseconds. So basically, this is the solution for problem. Is there any question to ask? Or anyone want to ask any question? If no, then I think we can end 3 minutes early today. Let me just stop sharing my screen. No question. Okay, great. I think a lot of you are like very good at Leetcode. Probably even better than. Okay. Yeah. Let's just see. Let's just make like a poll before I end. So if you understand, rate. Let me just put an emoji. Rate. Rate. Let me just reaction. So if you understand, give a thumbs up If not, just rate a thumbs up. Yeah. Seems like it's very easy. Palindrome is quite easy. Maybe next week we can do it even harder. This may be not related to the solution. Just now we need to use long to the size of it. But why the data type of x can be not long? Okay, because if I come back I need to share my screen first. I'll answer your question first. Okay. So the reason why x we need to be long is like we how to say we do this operation, right? We times 10. So times 10 can result in a very big number. Like if you do like 1 2 3 4 5 times 10, it become like 1 2 3 4 1 2 3 0. It's another thing. So it can go over the limit. So 2 to 32-bit integer 2 to the power of 32. I think it's around, let's just check this. 2 to the power of 30. It's this number, right? So yeah, so it's this number. So it's this number. So if our integer, let's say x maximum integer, we maximum can hold this number. So let's say the input is this then we come here then we do this reverse times 10 then the integer overflow already because if I times 10 then it cannot hold anymore. So that's why like for the reverse we need long, or actually you just one long is, but then normally we just use long. So long if I'm not wrong it's 64-bit or it's 128-bit. I'm not sure already. You have to check that on yourself. It's because we have this reverse times 10 operation. That's why we need the reverse to be long. Basically that's the reason why. Yep. So is there any question? If not, then I think we can discuss today. Oh, so we actually end on time, on 10 p.m. Okay. Sure, no problem. See you all next week then. Bye everyone. Thanks for joining.